Okay, let's unpack this. Have you ever tried juggling 3 balls at once? Seriously, it's not easy,
It's
Ron.
definitely not my hidden talent.
You might get 2 going smoothly, keeping them in this nice, predictable rhythm. Easy enough. But then you throw in that third one.
Ah, yes, the troublemaker.
Exactly.
Yeah.
And suddenly everything just feels off balance. That
Hmm.
simple, elegant rhythm you had, it's just shattered. And all 3 balls seem determined to, defy you, threatening to crash down.
Mm-hmm.
Now imagine those balls aren't just, juggling props, but these massive celestial bodies. Planets, maybe moons, or even stars.
Yeah.
And each one is pulling on the others with this invisible, but incredibly powerful gravitational force.
Right.
It sounds almost like a fun little thought experiment,
Right.
but it gets really deep, really
Yeah.
fast. It becomes this fundamental challenge, right at the heart of how we understand the universe.
What you're describing so vividly there is essentially the core of what scientists call the three-body problem. And it's really not just some abstract puzzle, it's a foundational challenge. It sits right there in classical physics, in astronomy, and it's stumped some of the smartest people for centuries.
Centuries, wow.
Yeah, and what's truly fascinating here, and what we really want to dig into in this deep dive, is how adding just one more body, something that seems so simple, right,
Just one more.
can transform a system that was perfectly predictable, beautifully harmonious, into one that's profoundly unpredictable, often surprisingly so. So our mission today really is to guide you through this complex dance of these objects. We want to explain why predicting their future movements when you've got 3 or more is just so incredibly tricky.
Okay, lay it on us.
We'll look at why there's no simple general formula for it. And maybe most importantly, why understanding this seemingly abstract problem actually matters a lot, not just out there in space, but right here in our real world.
Got it. So this deep dive is basically our shortcut to really getting our heads around this complex idea.
That's the plan.
Fantastic setup. And,
Yeah.
To really appreciate just how wild and, chaotic the three-body problem is, I think we absolutely have to start by looking at its calmer cousin, right? The two-body system.
Exactly. You need the baseline. You need to set the stage before the main drama unfolds, as you say.
Right. So think about our Earth and the Moon, our good old Moon.
Yep. Classic example.
They're locked in this incredibly neat, repetitive dance. It's like a perfectly choreographed gravitational ballet around each other.
Mm-hmm. Very predictable.
The Earth pulls the Moon pulls the Earth, and because it's just the two of them, their interaction is remarkably, straightforward, consistent.
No outside interference, essentially.
Exactly. No other big players messing up the gravitational tug of war. They just orbit their common center of mass, and each one traces out this elegant, predictable ellipse.
Billions of years of the same dance steps.
Yeah, it's this cosmic ballet that's been repeating the same graceful steps for billions of years. It really shows you the elegant simplicity that can exist out there.
Indeed. And that elegance is absolutely key. In a two-body system, the real beauty, I think, lies in its perfect predictability.
Okay.
For centuries now, ever since Isaac Newton gave us the laws of universal gravitation, we've known that physics gives us what we call a closed-form solution for a system like that.
A closed-form solution, what does that actually mean, in simple terms?
Think of it like a straightforward algebraic formula, like the ones you learned in school. If you know the masses of the two objects, their current distance apart, and how fast they're moving.
Their velocities, right?
Right, their velocities. You can plug those numbers into a neat equation and bang, it tells you their exact positions at any point in the past or the future.
Any point, perfectly.
Perfectly. It's not an approximation, not a guess. It's a precise, direct, finite calculation. That's exactly why we can predict things like tomorrow's sunrise down to the second, or the exact timing of a solar eclipse decades, even centuries from now, or plot the precise orbital path of a satellite going around Earth.
Okay, that makes sense.
The mathematics behind it provide a complete and general solution. It's kind of like knowing what 2 + 2 equals.
Right.
You don't need to guess or simulate it or run some huge program. You just apply a simple, direct calculation, and you get 4 every time.
Okay.
That's what a closed-form solution gives you for two celestial bodies. Because it's just two, their gravitational interactions are contained, they're consistent, and that allows for this precise, general mathematical solution that holds true over immense stretches of time. It makes these systems wonderfully predictable. It's really a cornerstone of celestial mechanics.
So it's easy then, relatively speaking, in the grand scheme of cosmic math.
Well, easy might be strong for some of the calculations, but conceptually, yes. Predictable.
And that predictability is almost comforting, isn't it? It gives you this feeling that, okay, we've got a handle on the universe. It operates on these beautiful, simple rules like clockwork.
Yeah, a very deterministic view.
You can just write down an equation,
Mhm.
plug in the numbers, and boom, you know exactly where everything will be perfectly.
Yeah.
But, and here's the big but, right? Here's where it gets really interesting and maybe a little bit unsettling.
Oh,
What happens when you toss in that third planet or maybe another star? What happens when you throw that into the perfectly choreographed two-body dance?
yeah.
It is just a case of adding more variables to the equation,
Mhm.
making it a bit harder, or does it fundamentally change the whole game? Does it break that elegant predictability we were just talking about?
It's definitely not just adding another variable. It's a profound shift, a qualitative change. And that
Yes.
is precisely when the dance gets messy.
Messy. Okay.
Wonderfully complex, often chaotic, messy. The fundamental change is this. Now everybody pulls on the other two.
Ah, okay. Not just one-on-one.
Exactly. Think about it. Planet A pulls on B and C. Planet B pulls on A and C. And Planet C pulls on A and B.
Right. It's a free-for-all.
It creates this gravitational tug of war that's no longer simple or isolated. Instead, the forces are constantly changing, constantly readjusting in these unbelievably intricate ways, because each body's movement immediately influences the forces acting on the other two,
Right.
which then influences their movements and so on and so on. It's this continuous interdependent feedback loop.
Oh.
The forces are dynamic, they're mutually influencing each other, and they just spiral into unpredictability. So, unlike that neat, predictable, closed-form solution we have for two bodies, for three bodies, there is no single neat algebraic formula, no magical universal equation that can predict their future movements with perfect precision over long periods.
No magic equation. No.
And believe me, it is not for lack of trying.
I bet.
Some of the greatest mathematicians and physicists in history have wrestled with this for centuries. Newton himself struggled with it, trying to figure out the moon's slightly wobbly orbit around Earth because the sun pulls on it too.
Ah, so even Earth, Moon, Sun is a three-body problem.
Absolutely. It's a classic, albeit one where the sun's influence is perturbed but doesn't totally destabilize the moon's orbit in the short term. Later giants like Euler, Lagrange, Poincaré, they all tackled it. But the reality is, a general closed-form solution for just any old three-body setup simply doesn't exist.
So what do scientists do instead? Just give up?
No, not at all. Instead of a simple formula, they have to use really powerful supercomputers.
Okay.
And these computers simulate the system by making incredibly precise calculations, updating them repeatedly over tiny, tiny fractions of time, little baby steps.
So it's a fundamentally different approach then, not just harder math.
Fundamentally different brute force computation instead of elegant equation.
That's a really powerful distinction. It means we can't just, scribble one equation on a napkin and know what's going to happen in a million years with total certainty.
And nope, that dream died.
It's like that analogy we touched on earlier, the three friends on a dance floor.
Yeah, I like that one.
Instead of two friends doing a perfectly synchronized tango where you know their steps relative to each other,
Predictable.
now all three are trying to, pick partners randomly, changing who they're interacting with and how strongly at every single step based on where everyone else just moved.
Constantly shifting dynamics.
Imagine trying to predict the full choreography of that dance from the very start. Every single step changes the story for all three dancers, who they'll partner with next, how they'll move.
Right.
It makes it utterly impossible to predict the whole long-term dance from the beginning. You might know the first few steps, maybe even the first few minutes, but beyond that, it just becomes this chaotic tangle of movements.
Yeah.
Impossible to map out precisely way in advance.
And that analogy really hits the nail on the head.
Hmm.
Because it's not just hard, say, a really complicated calculus problem is hard but solvable if you're smart enough and have enough time.
Okay.
It's fundamentally mathematically impossible to find a universal, neat formula for the general three-body problem.
Impossible. Not just really, really hard.
Impossible in that specific sense. Let's go back to that idea of a closed-form solution.
Right, the neat algebraic formula.
Exactly, like 2 + 2 = 4, or the formula for the roots of a quadratic equation. Direct, finite, elegant. For two bodies, these exist. We've got them.
Yep.
But for three bodies, well, there was this groundbreaking realization, maybe even a bit shocking, back in the late 19th, early 20th century.
Okay, this sounds important. This is the aha moment you mentioned. Because it's not just that we haven't found the formula yet, it's that one provably can't exist in general.
Precisely. It's not about human limits or our computers not being powerful enough yet. It's about a fundamental, provable mathematical truth. It sets a hard boundary on what is knowable through that kind of formula.
So what happened? Who figured this out?
It wasn't just a feeling or an unsolved puzzle. It was a definitive proof, a mathematical wall, you could call it. Mathematicians like Heinrich Bruns and maybe most famously Henri Poincaré.
Poincaré, I've heard the name.
A giant. He was working on a prize problem, actually, set by King Oscar II of Sweden and Norway. The question was about the stability of the solar system, a many-body problem, really, but the three-body problem is at its core.
Okay.
And Poincaré showed that the general three-body problem exhibited what he called non-integrability.
Non-integrability. Fancy term. What does it mean?
It essentially means you cannot write down the positions and velocities of the three bodies at any future time using a finite combination of standard mathematical functions, things like polynomials, sines, cosines, exponentials, logarithms, the usual toolkit.
Huh. So the tools we normally use to describe motion just don't work here.
Not in a general, finite, closed-form way. It's not about the complexity making the formula super long. It's that such a formula built from those standard blocks simply cannot be constructed for the general case. It's a fundamental mathematical impossibility. Think about the philosophical shock this caused. For centuries, people viewed the Newtonian universe as this grand, predictable clockwork, perfectly deterministic.
Right. If you knew the starting point, you knew everything forever.
Exactly. And Poincaré's work proving this inherent non-integrability and also discovering the concept of sensitive dependence on initial conditions, which we'll get to.
Okay.
It fundamentally challenged that deterministic worldview way before quantum mechanics came along with its own kind of uncertainty.
Wow. So even classical physics has this deep well of unpredictability built into it.
For systems with three or more interacting bodies, yes. No matter how smart you are, no matter how big your supercomputer, you will never find that single magic formula that works for all possible three-body setups. It's provably unsolvable in that general algebraic sense.
Yeah.
A mathematical limit found, defined.
Okay, mine's slightly blown. So if there's no magical universal equation, if we can't just plug numbers into a formula and leap decades into the future,
Yeah.
how on earth do scientists actually track these systems?
Yeah, good question.
How do they plan incredibly precise space missions, like sending a probe to Mars? There's the Sun, Earth, Mars, Jupiter's pole. Definitely more than two bodies involved there.
Absolutely.
Are they just, I don't know, winging it? Throwing darts at a cosmic dartboard and hoping for the best? That sounds risky for a billion-dollar mission.
Yeah, definitely not winging it. Far from it. While there's no general closed-form solution, that absolutely doesn't mean we can't make highly accurate predictions for specific scenarios over specific, relevant timeframes.
Yeah. Oh.
This is where numerical solutions and numerical integration become the heroes. They are the workhorses of modern space exploration and astrophysics.
Numerical solutions.
Oh, yeah.
Right. The computer simulations you mentioned.
Exactly. Instead of finding that direct formulaic path to the end, which we know doesn't exist in general, we use powerful computers to simulate the system step by step.
Baby steps.
Tiny baby steps. Imagine you want to plot a spacecraft's path over a year. You don't have a formula to jump straight to its position in 365 days. No. Instead, the computer calculates its position after, say, 1 millisecond or even less, considering all the gravitational pulls acting on it at that precise instant. Okay. Then, it uses that new position and velocity to calculate where it will be after the next millisecond, and the next, millions, billions of times.
So back to the maze analogy. Instead of seeing the whole map and drawing a line to the exit,
Which you can't do.
You're literally taking one tiny step, looking around right where you are, seeing how all the complex forces are pushing and pulling you right now, deciding your next minuscule step based on that, and then just repeating that process over and over and over.
That's a perfect way to put it. It's a relentless, precise crawl through the possibilities rather than a confident leap based on a known formula.
A crawl, okay.
And each tiny step is a full recalculation based on the new, slightly shifted positions and velocities of all the interacting bodies. Everything affects everything else constantly. Now, here's the crucial part, the catch, if you will.
There's always a catch.
While this method lets us predict the motion of planets or spacecraft with incredible accuracy, good enough for all our missions, it's still only approximately precise over very long time scales.
Why only approximately? If the computer is doing exact calculations at each step.
Well, two reasons mainly. First, Computers don't use infinitely precise numbers. They have a limit to the number of decimal places they can store what we call finite precision arithmetic. So tiny rounding errors creep in at every single step.
Okay, rounding errors.
Second, we're approximating continuous motion, which is smooth, with these discrete, tiny time steps. Even if the steps are incredibly small, it's still an approximation of reality.
I see. Little jumps instead of a smooth flow.
Exactly. And each minuscule simplification, each tiny truncation error, when you compound it across billions or trillions of calculations needed for simulations over millennia or eons, they inevitably add up. They cause the simulation to drift, slowly but surely, away from the true, infinitely precise trajectory the real system would follow.
Like trying to draw a perfectly straight line across a huge map with a ruler that's just slightly warped.
That's a great analogy. Even if your hand is super steady, those tiny imperfections in the ruler mean that by the time you get to the other side, you're noticeably off course.
Okay.
So for practical purposes, like getting a probe to Jupiter, these numerical simulations are fantastically accurate. They're excellent approximations for the foreseeable future.
Good enough.
But they aren't perfect, infinite prophecies like a true closed-form solution would be. And that inherent limit comes directly from the nature of the three-body problem itself.
And this accumulation of tiny errors, this drift, this is where the chaos idea really kicks in, isn't it?
Bingo.
It leads straight to that famous, maybe slightly overused phrase, the butterfly effect.
It does. And it's not just a loose metaphor here. It's deeply mathematically real in these systems.
It feels almost terrifyingly literal when you talk about planets potentially crashing because of a microscopic difference at the start.
It is pretty mind-boggling. What we're talking about formally is sensitive dependence on initial conditions. It's a cornerstone of chaos theory.
Sensitive dependence on initial conditions.
Okay.
What it means is that even the smallest, tiniest, almost imperceptible change in the starting positions or velocities of the bodies can lead to wildly, astronomically different futures for the entire system down the road.
How different are we talking?
Let's use a classic thought experiment. Imagine two super detailed simulations of a hypothetical three-star system. In simulation A, you set everything up as perfectly as humanly possible.
Okay.
In simulation B, it's identical, except you nudge one star's starting position by just the width of a human hair. An infinitesimal difference, smaller than anything we could ever actually measure in reality.
Right. Impossible to even detect.
Now, you let both simulations run on your supercomputer for, say, 100 million years. What do you see?
I'm guessing not the same thing.
Not even close.
Yeah.
Over that vast stretch of time, the two simulations, which started out practically identical, can end up looking completely fundamentally different. In simulation A, maybe the planets are still orbiting nicely, maybe a bit wobbly, but stable.
In simulation B, that tiny initial nudge, amplified over millions of years by the chaotic interactions, could lead to total catastrophe. Maybe a planet gets ejected entirely, flung out into the cold darkness of interstellar space.
Whoa.
Or maybe two planets collide in a cosmic smash-up, or one spirals into its star. The end states can be radically different because of that initial microscopic difference.
That is utterly mind-bending. It means forecasting the long-term future of these systems is basically impossible beyond a certain point.
Practically impossible, yes.
Because we can never know the initial conditions with infinite, perfect precision. There's always some tiny margin of error, some uncertainty in our measurement.
Always. Measurement limits are fundamental.
So the universe at this level isn't just complicated, it's fundamentally chaotic in its long-term predictability. Absolute certainty about the distant future just isn't on the table for these systems.
It's a profound humbling, isn't it? It challenges our desire for perfect prediction. The implications of this inherent chaos are huge, and they go way beyond just math or navigating spacecraft. It tells us something deep about the limits of prediction, even in systems governed by seemingly deterministic classical laws.
Okay, so bringing it back down to Earth, maybe.
Yeah.
What does this all mean for us? Why should listeners, who aren't planning space missions, care about this abstract physics problem? Especially if there's no perfect fix anyway.
Yeah, fair question.
It sounds like something astronomers need to worry about, but does it connect to our lives or our understanding of things more broadly?
Oh, absolutely. It's far from abstract when you look at the implications, both practical and, well, almost existential.
Okay.
First, let's stick with the practical. Astronomy and space missions. Understanding this is absolutely non-negotiable. It's a practical necessity.
Right, you need those simulations.
Planning spacecraft trajectories demands incredibly precise numerical simulations. We push our computers to the limit. Every single mission we launch, sending probes to Mars, Jupiter, Saturn, navigating complex paths to visit comets, even just tracking asteroids that might pose a threat to Earth.
Yeah, that seems important.
All of it relies entirely on these complex, step-by-step numerical calculations that account for multiple gravitational pulls. Without them, missions would just fail spectacularly.
Okay.
We need these iterative calculations to make sure our probes actually reach their targets, get into the right orbit, and avoid smashing into things. Think about the gravitational assists, the slingshot maneuvers that missions like Voyager or Cassini use.
Right, using a planet's gravity to speed up.
Exactly. Those wouldn't be remotely possible without incredibly detailed, constantly updated numerical models that account for the sun, the target planet, the spacecraft, maybe even other nearby planets. It's the difference between hitting a specific arrival window at Jupiter and, well, missing the solar system entirely.
So pretty critical for exploring space.
Absolutely critical. But it also has these huge implications for the stability of planetary systems themselves on a much grander scale.
Right. You mentioned the science fiction connection earlier.
Yeah.
That novel, The Three-Body Problem.
Exactly. Lou Schlickson's novel uses this physics concept as its central premise. And it's not just a cool science hook. It drives the entire plot, the entire civilization's history.
How so?
In that fictional world, there's a planet orbiting 3 suns. And because of the three-body dynamics, those 3 stars create utterly unstable, chaotic, and completely unpredictable conditions on the planet.
Unpredictable climate.
Worse than that, unpredictable everything. Their combined chaotic gravitational pulls mean the planet's orbit is constantly changing wildly. Sometimes it gets flung too close to one star and freezes over. Other times it gets scorched near another. Sometimes it's stable for a while, then suddenly thrown into a crazy elliptical path.
Wow, living there would be stressful.
To say the least. The civilizations that rise on this planet are constantly facing extinction. They have these cycles of destruction and rebuilding, not because of war or politics, but because their entire environment is fundamentally chaotically unstable due to the 3-body dance of their stars. It's impossible to plan long term.
That's terrifying.
Yeah.
It shows the profound existential impact this physics can have. It literally dictates habitability and the fate of civilizations.
Precisely. It paints this vivid picture of ultimate environmental instability.
Gives me chills just thinking about it.
Yeah.
And you also said earlier that this isn't just about huge planets and stars. This same dynamic, this 3-body thing, applies at much smaller scales too.
That's correct. And sometimes that's even harder to wrap your head around.
Yeah, like how small are we talking?
Down to the level of atoms. The 3-body problem, or maybe more accurately, the mathematical non-integrability that pops up with 3 interacting things, isn't just a cosmic phenomenon. It's a fundamental feature of complex interacting systems at all scales.
So like inside an atom.
Yep. Think about, say, a helium atom. You've got the nucleus, and then 2 electrons orbiting it. That's essentially a quantum 3-body problem. Okay. Now, the physics governing it is quantum mechanics, not Newtonian gravity, obviously. But the underlying mathematical challenge has similarities. Trying to perfectly describe the behavior of those 3 interacting quantum particles with a simple, general analytical formula, turns out you can't really do that either.
Huh. Same problem, different physics.
Conceptually similar challenge. The interactions between those 3 quantum particles create this complex, interdependent system. We need sophisticated computational methods, approximations to understand their dynamics, much like with the planets.
So it really is universal.
It illustrates that this inherent unpredictability, this complexity that emerges when you go from 2 interacting things to 3, is just deeply baked into the fabric of our universe. From galaxy clusters down to subatomic particles, it highlights this universal limit on exact analytical prediction.
Okay, so after all this discussion about impossibility, chaos, limits on what we can know, I have to ask, is it always impossible? Like, is there literally no exception where you can get an exact, neat, closed-form answer for 3 bodies?
Ah, good clarification. That's a really important point of nuance.
Because it feels a bit bleak if everything beyond 2 is just chaos and approximation forever.
Right. No, it's not always impossible. There are indeed some special cases, highly specific, usually highly symmetrical, constrained configurations where exact analytical answers do exist or where the problem simplifies enough to become solvable.
Okay, so there are loopholes.
Sort of. They happen under very specific conditions. Usually it involves exploiting some symmetry in the setup or making certain justifiable assumptions.
Like what? Give me an example.
Well, remember we talked about how messy it gets when all three bodies pull on each other significantly?
Yeah.
What if one body is incredibly tiny compared to the other two? So small that its own gravity basically doesn't affect the big guys, but it definitely gets pulled around by them.
Like a tiny speck of dust near two big stars.
Exactly, like a tiny asteroid orbiting two massive stars that are mostly just orbiting each other, barely noticing the asteroid. In that case, the asteroid is like a test particle. It just responds to the gravitational field set up by the two heavyweights, but doesn't really change their dance. That simplifies things hugely.
Okay, that makes sense. The restricted three-body problem, is that what it's called?
That's one version of it, yes. And within these simplified scenarios, you can find exact solutions. A famous early one is Euler's collinear solution. He showed that three bodies, even of different masses, could theoretically stay in a perfectly straight line if they started with just the right positions and velocities relative to each other.
Huh. Balanced perfectly in a line. Seems unstable, though.
Often they are unstable, yes. A slight nudge and they fly apart, but the mathematical solution exists.
Are there any of these special cases that are actually, like, useful, stable ones that matter for space exploration or understanding real systems? Because Euler's line sounds pretty theoretical.
Absolutely. They might be rare compared to all possible random setups, but some special solutions are incredibly important. The most famous and useful are definitely the Lagrange points.
Lagrange points. L points. I think I've heard of those.
That's them. Named after Joseph Louis Lagrange, another mathematical giant who studied the three-body problem. There are 5 specific points in space relative to 2 large orbiting bodies, like the Sun and the Earth, or the Earth and the Moon.
5 specific spots?
Yes. At these 5 points, the gravitational pull from the 2 large bodies, combined with the centrifugal force experienced by a third, much smaller object, all balance out in a special way. This means a small object, like a spacecraft or an asteroid, placed at one of these L points, can maintain a stable or semi-stable position relative to the 2 big bodies.
Like it's hovering there, or orbiting with them.
Kind of orbiting with them, yeah. It stays in the same relative position. Think of them like gravitational parking spots in space.
Cosmic parking spots. That's amazing, and we actually use these.
Absolutely. They are crucial for modern space science. For example, the James Webb Space Telescope, our most powerful space telescope.
Yeah.
It's parked way out at the Sun-Off L2 Lagrange point. It's about 1.5 million kilometers away from Earth on the side opposite the Sun.
Why put it there?
It's a fantastic spot. It allows the telescope to keep its back to the Sun, Earth, and Moon simultaneously, so its sun shield can protect its sensitive instruments from their heat and light. It also requires very little fuel to maintain its position there, making the mission last longer. It's a gravitationally stable-ish location.
Wow. Okay, what about the other points? L1, L3, L4, L5.
L1 between the Earth and Sun is great for solar observatories like SOHO, giving them a constant view of the Sun. L3 is on the far side of the Sun, harder to use. But L4 and L5 are really interesting. They form equilateral triangles with the 2 large bodies.
Okay.
And these points, L4 and L5, are truly stable. They're often called Trojan points.
Trojan points, like the Trojan asteroids.
Exactly. Jupiter has huge clouds of asteroids trapped gravitationally at its L4 and L5 points, preceding and following it in its orbit around the Sun. We call them the Trojan asteroids. Neptune has Trojans too. Even Earth has at least one known Trojan asteroid sharing its orbit. These points are like natural gravitational wells, trapping objects for billions of years.
That's incredible. So nature found these stable solutions to the three-body problem and actually uses them.
Nature found them, yes. Or rather, objects naturally collect there. It's a perfect example of finding order within the chaos. It shows how understanding these specific solutions lets us navigate and even exploit the complex dance of celestial mechanics.
So it's not all chaos and approximation then. There are these elegant exceptions.
There are elegant, mathematically precise exceptions, but for the general case, the random case of 3 comparable masses starting in arbitrary positions, we're still fundamentally reliant on those numerical methods, those step-by-step approximations. The general problem remains analytically unsolvable in that closed-form sense.
Okay, let's try and wrap this up then. This deep dive into the three-body problem. Wow. It's definitely been a thought-provoking ride. It really forces you to rethink basic ideas about prediction and order in the universe.
It really does.
We started off appreciating that nice, simple, two-body system. Predictable, formula-driven, almost like clockwork. Thanks,
Yeah,
Con.
the good old days.
But then we tossed in that third body, and boom, everything changed. We learned the three-body problem is just fundamentally hard. There's no single, neat, one-size-fits-all formula to solve it perfectly for every situation.
And critically, not just hard, but proven to be analytically unsolvable in general by mathematicians like Bruns and Poincaré, that really shifted the deterministic worldview.
Right. And we learned that while our amazing supercomputers are essential tools, letting us approximate solutions by doing billions of tiny step-by-step calculations.
The numerical integration.
Those solutions, even though they're incredibly accurate for planning missions and stuff, they're never absolutely perfect over really, really long timescales.
They're always approximations in the long run. And crucially, they're incredibly sensitive to the starting conditions. Even the tiniest unmeasurable difference at the start can lead to completely different outcomes later on. That's chaos theory in action.
Yeah, it really shows how the universe can seem so simple and elegant with just two parts interacting, but yet just one more, and it becomes this wild, weirdly chaotic, fundamentally unpredictable system, at least in the very long term.
It's a powerful lesson, even in a universe governed by deterministic laws, like Newton's gravity. You can still get profound unpredictability emerging purely from the complexity of the interactions.
So here's maybe a final thought for you, our listeners, to chew on after this deep dive. This core idea we kept coming back to, sensitive dependence on initial conditions, the butterfly effect. Tiny differences at the start blowing up into huge differences later. That's not just about planets and atoms, is it? Think about other really complex systems you encounter every day, systems that seem to defy easy prediction, like your local economy, maybe. So many businesses, consumers, banks all interacting. Or how trends suddenly take off on social media. Or even how big geopolitical events unfold a small incident somewhere, triggering massive consequences.
Yeah, complex systems everywhere.
So how might understanding this three-body problem maybe as a metaphor for any system with multiple complex interactions and grasping this deep concept of chaos? How might that help you see the hidden unpredictability, the potential for sudden shifts in other parts of your life? Could it make you a bit more prepared for the unexpected, maybe? Or just more appreciative of how complex and interconnected everything really is?
That's a great question to ponder. Seeing the potential for chaos in everyday complexity.
Something to think about until our next deep dive.